Hello everyone, this is Pranay from Electrical Department, and now we are going to discuss about how to design BGA circuit and simulated cadence. Firstly, BGR is short for band replacement circuit, and it is used in power management blocks in analog as well as digital circuits. Now we will see the block diagram of BGA circuit. Yeah, as you can see, this is the BGR block diagram. So the first one, this BJT is connected in diode fashion, and then the voltage dropped across the BJT when constant current is pumped in will be complementary to absolute temperature. That means the slope of the curve with temperature decreases at a rate like here it is minus 2 millivolt per 1 degree Celsius. Similarly, by using two CTAT sources that is complementary to absolute temperature, we can generate a PTAT source which will increase with increase in temperature. So it is called proportional to absolute temperature. So here the rate of increase is 85 microvolt per degree Celsius. Now we can observe that one of the voltage curve is decreasing with temperature and another is increasing with temperature. So if we find a way to add those two, so we'll get a voltage which is constant with like over the complete temperature range. Uh, yeah, so that's how Bezier works. So I will show you the cadence simulation of this Bezier circuit, the PTAT and CTAT voltages, and then I will show you how I added those two to get the reference voltage. Yeah, so this is the schematic. Yeah, this is the schematic of the BGR circuit. Now, as we can see, I've connected the BJT in diode fashion, and then I'm pumping a constant current into the BJT. So yeah, so we'll get a CTAT voltage and at this node. Similarly, from a class we have been taught that if we maintain the voltages across this and this node as the same, then this node is like it is also CTAT since we connected to diode connected BJTs. So the difference between these two will give you a PTAT voltage. That's what I mentioned here. Like the one is PTAT, sorry, one is CTAT, and another one is scaled version of CTAT, which is I've connected that with two different, sorry, two same diodes. So I'll get a PTAT from that circuit. So I'm maintaining these two voltages at the same level using the current set the current mirror load, and then I'm at the end the voltage across this resistor will be PTAT, and then I'm so since resistor is a linear element, the current through the resistor also will be PTAT in nature. So I'm mirroring that current into next branch. So this current will be PTAT, so that the voltage drop across this resistor will be PTAT. And then I'm connecting the that connected BJT again. So from the ground, we'll get a CTAT voltage difference from ground to this point, and from here to here, we'll get the PTAT since the current is PTAT. So at this node, we'll get the reference voltage. Uh, so I'll show you the simulations that I've done for obtaining these results. Yeah, since yeah, one more thing. The CTAT voltage is slope is at minus 2 millivolt, and then the PTAT slope is at plus 0.85 millivolt. So there is you can see a large difference. So by adding these two also will not give you a constant reference. You have to scale this one up or this one down. I've chosen to scale PTAT up. So and then that can be controlled by the ratio of these two resistors, and then a number of multipliers like the number of diodes which we connected and parallel to this. So I've taken a 3K, this is as 3K, and this resistor is 105K. Like I've done the calculations for getting a constant reference voltage of 1.1 volt. Yeah, so yeah, first I'll show you the CTAT voltage across this node, and then I'll show you that these see this node and then this node are at the same voltage level. And then this node, so the difference between these two will give you PTAT. So VCTAT is CTAT, and then VNCTAT is this node. So sorry, VNCTAT 1 is at that node. And the difference is PTAT list. We'll plot them. Yeah. So yeah, so we can see that VCTAT and VNCTAT they are approximately close to each other. And then VPTAT is rising, like it has positive slope, and VCTAT is having negative slope. So yeah, so by mirroring the current into this resistor, then by keeping a CTAT source like diode, we can get a reference voltage here. So I'll show you that. This is the PTAT, this is CTAT, and this is the output. Like PTAT is the difference between these two nodes. CTAT is the voltage at this node, and then the output is the voltage at this node. So we know the others. Yeah. So as you can see, the PTAT, CTAT, and then the output. The three plots are there in this figure, and we can fairly observe that the rate of decrease and the rate of increase are approximately equal. Then we're getting a constant output voltage from across the temperature. So by splitting them into steps, we can see that yeah, this is the output voltage. It is like the maximum peak to peak variation in the voltage that I've calculated here. Peak to peak output, that is around, yeah, sorry, the system got disconnected from the system server. So yeah, resuming from the point. The PTAT and the CTAT curves are shown here, and then the maximum ripple is 3.45 milli. And then I said that I have designed this BJ circuit for 1.1 volt, steady 1.1 volt for the complete temperature range. Temperature sweep I've taken is from -40 to 120. And then the whole process node which I've taken is JPDK 180 nanometer. So I'm getting a average voltage of 1.13 volt. So yeah. So this is the like we used a current mirror to maintain these two voltages at the same level. Then I've used another current mirror branch to get the V reference by just like I've kept two voltage sources in series. Like this will give you a CTAT voltage from ground to this point, and then across the resistor, since the current through the resistor is PTAT, you'll get voltage drop across the resistor is also a PTAT. And then the slope of the PTAT curve can be controlled by this resistor, and then the number of diodes, like diode connected BJTs in this branch. And one more thing, the number of diodes, like the parallel diodes, which are connected in this branch, should be even number to ease out the fabrication process. Yeah, I hope this was useful. It gave you some insights regarding designing a PJ circuit. So, thank you for listening.